frequency. So we know that C equals lambda nu, right? You guys remember us talking about that?
Yes.
Issues where nu is frequency. Lambda is wavelength. And C is the speed of light. Okay. So this allows us to calculate the frequency, right? So if you guys are getting the wavelength from the data that you guys are collecting, the speed of light is always going to be the same. Energy always travels at the same speed. It's 3 times 10 to the 8th. So to keep your sig figs, put 3.00 times 10 to the 8th. And the units are meters per second. Often you have these guys in nanometers. So that means you have to change these into meters. And then frequency is always going to be 1 over seconds, or we call it hertz. And 1 hertz equals 1 over seconds. Okay. So calculating energy. Energy is going to be equal to Planck's constant times frequency, nu. So once you calculate the frequency, then you can calculate the energy. Planck's constant, make sure I say C equals. So Planck's constant equals, get the value. I got my little cheat sheet here. I always forget it. And it's 6.6 something. And then I always forget the number. 26 times 10.
You're underwater again.
Sorry, because I moved away.
Okay.
10 to the negative 35.
Wait, what's that after n? Or n equals, is that 6?
6.626 times 10 to the negative 35.
Okay,
I'm sorry,
got it.
that ends, then that's H.
That's H. Yeah.
That's an H.
Equals H.
Does that help?
Optical.
What was that?
Equals H. What is that? What's after H?
What do you
Not
mean?
that,
Oh, this here? That's new. That's the same thing as this. That's frequency.
Frequency. Yeah.
Okay, and so then that's joules.
I like that one.
Joules per second. And joules is normally the energy that we use, but if you do put it in electron volts, then that's fine too. I know the conversion.
Yeah,
Maybe.
I did electron volts. Yeah,
Yeah.
my bad.
That's right. So, but
Electron volts equals joules.
no, it does not equal joules.
Yeah, my numbers were a little smaller than that.
Yeah. So, well, this is just the value for Planck's constant, right? And so if you look at the units, right? So frequency is 1 over seconds, seconds cancels out, and you're left with just joules. So, and then here, I'll give you the conversion formula.
Dr. Henry, I have a question.
Yep.
I saw on a video that H is equal to 6.626 times 10 to the negative 34. It's the same as negative 35.
No, it is not the same as -35. Let me check, because like I said, I have to use my little cheat sheet, and you might be right.
Oh, okay.
Let me pull up my cheat sheet. So, yeah, even, even I can't remember all of the constants values. There's certain ones that stick to you, like Avogadro's number. You're right, it's 34.
Oh, okay.
34.
Let me fix that. Good job. So 1 EV is going to equal to
1 EV.
yeah, so that's electron volts is equal to wrong one. I know it's 10 to the 19th or something. -19th or something.
One 1.602 times 10 to the -19 joule.
Okay. Or 1 joule is equal to
Does that sound right?
6.24 times. Is that right? 6.24
1 electron volt?
times 10 to the, yeah, times 10 to the, no, actually, you're right. Hold on. So,
Says for an approximate result, divide energy value by 6.242 E plus 18.
okay, so 1 joule. So, sorry. Oops, 1.6.
02 times 10 to the -19. Yeah. Joule. Perfect.
And you guys can put those on your conversion sheets. So did you guys all print out your conversion sheets?
Mm-hmm.
So you can put this on there, and you can also put Planck's constant. And of course, the speed of light.
Okay, speed of light. Planck's constant.
Okay.
Hold up 1 second. I'm gonna screenshot it. Please don't take it
Okay.
away. So then I can write it down.
And
All right, I'm good.
and just to remind you guys, I am human. There will be mistakes. So anytime that you're like, well, I'm not sure, is that right? I saw it somewhere else. Ask, because sometimes when I write things down, I write down things, it'll be a mistake. I am human. I'm gonna make mistakes, but the goal is not to make in key points. So. Okay.
Brianna.
Oh, so
That-
it's EV. This is
Electron.
one. That's 1 EV.
Yeah.
So that's electron volt. Does that answer your question?
Yes, thank you.
No problem. Okay. Let's see. Now we can get to the lecture. Okay. Share screen. So Okay, so we were talking about the subunits. I'm trying to remember how far we got. So we talked about the subunits, the S, the P, the D, and the F.
Yep.
So do you guys remember how many electrons can the S orbital or the S sublevel hold?
2.
Okay.
2.
How many can the P hold?
6.
The D,
10.
And
the F,
14.
14.
okay? Good job. And if we had a G,
18. Probably 18.
that's good. And an H,
22.
22.
okay. So you guys can see that trend that's going on, right?
Yeah.
Okay,
Yeah.
so let's talk a little bit more about this, right? So in the S orbital, in the S sublevel, it has one orbital, right? An orbital can hold 2 electrons, right? So
Yeah.
in the P, it has 3 orbitals. So P has
Yeah.
3 orbitals.
3 orbitals.
It has 3 orbitals. And each orbital, as I said, can hold 2 electrons. So if there's 3, it can hold a total of 6 electrons.
Yeah.
The D has how many?
5.
The F would have how many?
7.
The G would have how many?
9.
And the H would have how many?
11.
Okay. So does that make sense?
Yes, it does.
Okay. So, and you guys are going to say, okay, I don't get it, right? Some of you guys may say that. So let me kind of put it in a different way. So, have you guys been to a movie theater?
Yes.
Yes.
Okay. And if you notice that most movie theaters, they have like in the front, they'll have 2 seats. They'll have a space where a person with who's handicapped could actually sit. And then they'll have 2 seats. And then they'll be, okay. So it's kind of like that. So that space where there's only 2 seats, that's kind of like the S orbital, right? So that would be the S orbital. The S sublevel. But those 2 seats represent a spot for each of the electrons in that orbital. So that there would be that S orbital, okay? The P has 3. So it'll be groups of 3 that are kind of together. So 2 here, 2 here, 2 here, right? And so that would be like your P. And then the 10 would be your D, where it has 10 seats, but groups of 2.
Oh, so they gotta make themselves fit somehow in the allotted spaces that are provided.
That is correct.
So some of them may be like double seating.
Okay. So let's see. Clear this. Okay, so are you guys kind of getting that right now? So that understanding of the different sub-levels and then the grouping of like the seats?
Okay, like I don't really get it, like because I'm trying to imagine in my head right now. So if the P has 3 orbitals and each orbital holds an electron, that means if an element has like the electronic configuration of 1s2, 2p6, 2s2, 2p6, blah 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 blah, and like all the way to like 4s, like you have to be like the amount of orbitals they have is times each one. I don't know if you're understanding me.
I'm not getting it, but I'm gonna see if I can help you out and grasp it
Okay.
a little bit.
Okay.
So okay. So for instance, here, this guy represents the 1s orbital. The 1s orbital can hold 2 electrons. So 1 electron will go in this way, 1 electron will go in that way. The 2s orbital can hold 2 electrons. One electron will go in that way, 1 electron will go in that way. The 2p electron can hold a total of 6 electrons. So we can have one that goes in this way, and then we'll fill it up this way, because you know how like guys that'll go to a movie together, they always like to leave a seat between them because they're hoping that a girl will come in and sit next to them, right? You guys seen that where a couple guys that come in together, they'll leave a seat between
I
them?
don't think that happens often though.
Really? Well,
I've
not
seen it, but
anymore
I-
because of COVID.
Yeah.
Okay, so then what happens is they come back in and then they fill in those other seats when they have to.
Okay.
Okay.
Yeah.
So this guy holds a total of 2 electrons. This guy can only hold 2 electrons. Well, the p can hold 6, 2, 4, 6, but only 2 in each of the p orbitals. Okay. Does that make
Okay.
sense?
It does.
Yeah, it does. Well, like so now this element, for example, would have 5 orbitals altogether.
So if it has, yes, it does. In the case, it does have
Okay.
5 orbitals that can only hold 2, but these
Okay.
guys are at different energy levels. So the way that we would plug these in is based upon energy level, and I'm going to show you that.
Okay.
So that was the next thing. And so when we're talking about those that level, the N, or what we call the principal number, that kind of represents our energy level, right? So when we talk about the 2s, the 2p, so 1s is lower in energy than the 2s, and the 2s is lower than energy than the 3s. Okay, so let's see, some questions here. Okay, so here, this is basically kind of showing you just the 3s part of it. So here we have 3s, then we'll have 3p, then we'll go up to the 4s, then we'll go 3d. So you have this overlap right here. But before this, we'll have the 1s and the 2s. And then you'll have 2p, where p would have those 3 orbitals. So technically you have 3 orbitals here for that 3p, okay? Oops. Okay, and then all of that will be below in terms of energy level. So in terms of our energy levels, everything is going to be organized in terms of energy. So when the electrons are entering, they're always going to try to enter at that lower energy level and build themselves up. So if we're talking about, let's say we're talking about aluminum. Okay, so I'm just going to go ahead and continue here rather than and ignore this part and just use this white space. So this guy would be 3s. Then we'll have the 3p. Then we would have 4s. And I'll show you this on the periodic table too. And then we'll have the 3d. I mean, the 3d. So if we were talking about aluminum, aluminum has how many electrons?
13.
It has 13 electrons. Al has 13 electrons. Okay, so the way it would enter it, it would go, there'd be 1 there, 2, then it goes up to that next energy level. 3,
3,
4, 5, let's see, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so lowest energy level. So these guys are low in energy. So it fills these guys up first, the easy one that fills up, and it goes up until to that next energy level. So everything is full. Does that make sense?
Why do they do that actually? Why don't they just like, why are they increasing in energy?
Because the goal is to try to keep the lowest amount of energy, right? So if I put it all the way up here, then it's too high, right? We want to keep it low energy. Electrons,
Okay.
I mean, just kind of like you, the atom is lazy. It doesn't want to use too much energy. And it also it wants to try to keep things kind of close to the nucleus so that it kind of keeps its orbit. And then if you have
Okay.
things too far away, it takes a lot of energy to
Energy.
come back
Okay.
here. You're getting it too far away, you know, fix that energy,
Yes.
right?
Yeah.
So it's kind of like, the nucleus is kind of like a mom that's trying to keep track of all of her kids, right? The
Okay.
more kids she has, the more energy it takes to keep track.
Oh yes.
Okay. Okay, so let me show you this on the periodic table, and so that you guys can kind of start seeing the correlation. Okay, so we had earlier, S,
2.
P,
D.
D, and F. And I showed you guys that 3D is here, 4F is here. Okay. So if you guys look here at the 4S, right? We start here. So if we say 4S, it goes 4S, then it goes 3D, and then it goes to 4P. So when I drew those energy levels, I'll draw them again. So we have 1S at the lowest, then we'll have 2S, then we'll have 2P, then we'll have 3S, then we'll have 3P, then we'll have 4S, then we'll have 3D. Okay, so 4S, 3D. So 1S, 2S, 2P, 3S, 3P, 4S, 3D. You guys see that?
Can we do a different color and can you go over it again?
Sure. Okay.
And
so
just
let's-
like touch where you're talking about, like touch this one and then this one with
okay.
the color.
So
we can
let
kinda
me
see.
give you an actual example. Let's say we had cobalt. Last time we did copper and I said cobalt. But we're going to do cobalt this time. So we're going to do CO. Okay, that's what we're going to do. We'll use a different color. Okay, so CO is going to go 1S, right? So that's 1S first.
Okay.
So we're going to fill in all the electrons. So one goes one way and one goes the other way. Then it's going to go. So we'll write this 1s2 because there's 2 electrons in that 1s.
Okay.
Okay. And then we go to the next part would be, and we're going to cobalt. This is our goal right here.
Right.
So then we'll go 2s. So one goes in one way, one goes in the other way. So we'll write this here, 2s. 2s2 because there's 2 electrons.
Okay.
Then we'll go 2p. 1, 2, 3, 4, 5, and 6. So the way that they would be entered, they'd go in one up, the next one goes up,
Carrying 2, 4,
the next one goes up, and then we come back, down, down, down. That's 1, 2, 3, 4, 5, 6. So that's 2p6.
Are those upside down ones?
No, they're arrows.
Oh,
They
okay.
represent the spin. So you have to be in the same orbital. One electron has to go one way, one electron has to go the other way.
Okay.
If they go the same way, it causes repulsion and it causes things to go crazy, causes an explosion.
Oh,
So they have to go opposite spins. Okay, so then we have 3s. Those 2 electrons. So 3s2. Then we have 3p. 1, 2, 3, 4, 5, 6.
2,
1, 2, well, 3, 5, 6.
Could you just double up at the same time, or is there a reason why you go back?
There's a reason why we go back, because there's a rule that it wants to have them all in an orbital first before it
Okay.
goes back.
The Hume's rule, right?
What was that?
The Hume's rule. The
Hunt's
Hume's rule.
Yes.
Oh,
that's right.
Hunt's. Okay,
Yes.
Hunt's.
Yep.
Mhm.
Okay, then we have 4s2.
Mhm.
And then we have our cobalt, right? So that's 1,
3.
2, 3, 4, 5, 6, 7. So we'll go 1, 2, 3, 4, 5, 6, 7. Okay, so then that's my 4s2. And then we have 3d7. Okay, so this here represents the electron configuration. This would be an energy diagram showing where all the electrons are at.
Okay, Dr. Henry,
Yes,
can you do the electronic configuration of a transition metal?
that's what we just did.
Okay, oh, okay, yes, okay. There's this thing about if it doesn't fill 10 MTS, I don't still get it. So I wanted you to like kind of demonstrate that. Yeah, but don't worry.
Yeah, so I know what you're talking about. So like for
Okay.
instance, copper. Copper,
Yes,
yeah, copper is an example where we would have an exception, right?
yes,
And I'll show you that here in a second. So,
Okay.
but before we get there, what we're going to do is we want to sit there and write this in a simpler form so that we'll be able to see how many valence electrons there are. So what we would do is to write this in a simpler form, all the ones that are before the noble gas, we're going to kind of capture as a noble gas. So I would go back to the nearest noble gas.
Mhm.
So what would be the gas before?
Argon.
Okay, so argon. So we'll put a bracket, argon. So basically what I'm saying is all of these right here, these guys are making up argon, right? Because argon stops at the 3p6, right?
Mhm.
So we're just representing all of that by argon. And then to save us some time, and then this is the guy. Okay, to save us some time, we can just write the 4s2, 3d7. Okay, now there's 2 that we do this to. One is that argon represents a core. So that guy, it's completely full. It's all happy. So you guys remember when we were talking about the noble gases, them being cool, it's like, they're the cool kids, right? Everybody wants to be like them, right? So in other words, this part is set. It's a core. So you don't want to mess that up because it's already perfect. That part is good. This part here, this guy isn't. It needs something else. It's going to either need to lose something or it's going to need to gain stuff to sit there and make it so that it's more stable. Okay, so right now it's like it's not perfect. It's not like a noble gas. So it wants to try to be like a noble gas. So it's going to try to find a way of doing that. So these guys are called valence electrons. And these electrons can be used for reactions. And that's what we want to use these electrons for reactions and not the ones that are already happy, right? These guys are not happy yet. They need to find out how many they need to get to be happy. Okay? Does that make sense?
Yes.
Okay,
Yes.
so to kind of address Mary's question, so we did copper yesterday. So copper, I'm going to write the short form of it. Copper is going to be Ag, meaning that it's going to be all of those, right? And then, in this case, we're looking for copper. On this one. So then we'll go 4s2. And then we'll go 3d9. Right? So you guys see 4s2, 4s2,
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we would expect it to be this. So what happens is that this energy level, the 4s and the 3d, they're like just a little bit apart. Now, copper really is like, you know, these two energy levels are a little bit apart. If I put a little bit in, I can get a little bit more stability out of it. So what it'll do is it'll actually go ahead and make it so that this guy has 10 because he needs one more, and then this whole thing would be completely full, and it'll make copper a little more stable, having this guy, this energy level, which is in the third period technically because it's 3D, completely full, and then just leaving one S, leaving one in the 4s. So what copper really does is this. So because remember when I told you that you have to have one in one spin and the other spin
Mhm.
opposite ways, that helps with stability. So
Yeah.
copper's like, hey, you know, I can get these guys completely stable by just removing this one electron and pushing it up.
Okay.
This one electron. So, and that's what it does. That's what it actually does. Now, on the exam, right? I'm really cool about this part, right? On the exam, if you give me what is going to be expected and then what is actual, if you give me one of those, right, I'll give you credit for it.
Okay.
Dr. Henry,
We talked about it in class. Yeah.
Okay.
how would a question like this present itself on the exam or on the homework? Would it just say find the valence electrons of copper or of zinc or whatever?
It would be something like, what is the electron configuration of
Okay.
copper? Yeah. Because again, this represents the electron configuration. So electron.
And do we have to give the shorthand with the noble gas first, or is
So
long?
if I'm asking you the question, I always I like the shorthand because it makes it easier for me to see it, right? And then I find that most students, they'll screw up down here, you know, rather than that last part. They always make mistakes down here. If you just remember, take a noble gas and then you just go to where that element is, then you usually don't make that mistake. So I like the shorthand for my purposes.
All right.
Right? But I can read them both, so I have no issues with it. I'll sit there and grade both of them. For your benefit, it's a lot easier, you know, especially when you start getting to the ones down here. And I love picking the ones down here, right?
Right.
Hey, Dr. Henry.
Yep.
Also, I can't just help it. Like when you talk about orbitals, I kind of imagine them like, okay, I would like to annotate this. I kind of imagine them like circles. Can you see what I'm drawing? I kind of imagine
She
them
wrote
like
on the board.
Yes.
Yeah. So like for instance, the S, right? So
Okay, yeah.
the S orbital, and don't worry, I'll show you a figure here in a second. So the S
Okay.
orbital is a sphere. So it's not really, initially we thought it was just circle, right? But that's not the way it works, right? So if you guys think about how the Earth orbits the sun, it orbits, right? That's when we think about orbitals. We think about it like that, right? But
Mhm.
reality, the way the Earth orbits the sun is not quite like that either, right? It's more of a three-dimensional type of orbit, right? So the S orbital is a sphere. And let me see if I can find the figure. So can I clear this and then we'll come back to another? Give
Yes.
you guys another
Yeah.
example.
Yeah.
We're pushing that time, aren't we? Too. Okay. Let's see.
And Dr. Henry, we can use this on the test, like if we write the S, D, P, F on our table of elements.
Yeah, so I always remember to write, I put my 3D down there. Yeah, so I'll let you guys do that. That's fine.
Okay.
You know, most people who don't understand this or who have trouble with it didn't write that down in the first place. So
Right.
And then P starts back at 1, right? Or it starts at 3.
P.
Well, no, so
Well-
there's 3D, P, and F, right?
Yeah.
yes,
So D starts at 3,
that's
But-
right.
P starts at 13, but you don't have to mark that.
What do you mean?
So S is 1 and 2, right?
Yep.
3D goes from 3 to 12.
Oh, so you're saying the groups.
Yeah, the groups.
Yeah.
When you indicate the group, it would start at 3, right? Like 3P, 1, 2, 3, 4, 5, 6, or whatever, because there's already these 2 over here.
Yes. Yeah, so this here, these guys represent the S shell over here.
Oh,
So that's
that'd be
the
like,
S subshell, right? So
Right.
this is gonna be your
Columns.
S, this is the P, right? So the ones that are over here, these are gonna be in the P. These guys here are gonna be in the P. Does that
Right,
make
so
sense?
my question is, why does that start with 3D then?
Because it's the process is called, or the term is called degeneracy. And
Right.
so what happens is, like, for instance, we start at the 1S, right?
Right,
Then we go to the 2S, right? And
right.
then we go to a 2P, right? So do we have a 1P?
No,
So there's no 1P, right? So
right.
then we'll go to the 3S, then we'll go to the 3P, and then we have, although it's not in order, we have a 3D. right?
3S, 3D, 2P. So, yeah, okay.
So then the next one would be 4S. There's a 4P,
All right, so
and
it's
there's
just,
also a 4D, and then we have the 4F. Remember,
so,
the 4 starts at F.
yeah, the coefficient is just the group that it's in then, right?
So the coefficient is the period that it's in, not the group.
Period, sorry, period.
Yeah,
Yeah,
so
right.
don't
Okay,
mistake those. Yeah, so it is the period, except for these guys. These guys are shifted one. So we shift this guy 1 down, right? So this is actually the 3D, right?
Right.
Not the 4, it's not the 4D. This
but you could have
guy's
like,
the 4D.
you could have like 6P4 or whatever, because that's in the P group on the 6th period.
Yeah, so we could have 6P, yeah,
But then just for the D group, it's shifted down 1 for the whole D group.
yes. And then it's shifted down 2 for the F group, right? Because then we have, because this guy, look at, this guy is 6, so this is 6S. And then we come down here to 4F. Then we go to 5D. So the F is going to be shifted 2. And
Right.
then, so you see, the D is shifted 1, the F is shifted 2. And then if we went to a G, then that means that it would be that next one. So if we went, let's say, we'd have 5S, right? 5P. There would be a 5D. There would be a 5F. And technically, there could be a 5G. We just don't have enough elements yet.
Right,
Okay.
5F would be that 7th period down there.
That's right. So this guy would be 5F.
All right,
Okay,
yeah, thank you.
no problem. Okay, so is that good? You guys are clear?
Yeah, I'm clear, except for the orbital stuff.
Okay, so we'll go back to your orbital question and then we're gonna
Mhm.
kind of wrap it up there.
Okay.
Clear this. Okay, so these are the actual shapes of the orbitals. So this is the S orbital. These are the P's, right? So each of the P's,
Okay.
so this is one of those P's. This is the other P orbital. This is the,
Okay.
okay? So all of the S orbitals are just going to be spheres. So this is their 3-dimensional structures. So that all it means is that those electrons are traveling in that shape, you know, and it's representing that entire shape.
Hmm. But I can't seem to picture it because, like, okay, let me annotate. Because I keep seeing it like this, like, okay, let's say what will I use now? Like this is like the s orbital here, and this like are like 2 electrons. And I come here, this is the p, and in my mind I'm kind of like feeling it
No, but it's not quite like that. So what's going to happen is, yeah, so that's what I'm saying right here. So this, you'd have 2 electrons here.
Okay.
There's going to be 2 electrons here. There's going to be 2 electrons here. There's going to be two electrons here. Okay, if they're
Wow.
completely full. Okay, so basically you'll have an electron and it's going to be following this orbit. Okay, and then you're going to have another electron going to be following this orbit. So if you kind of lay them on top of each other, they never intersect with each other, right?
Okay.
Because this is in the X plane, this guy is in the Y plane, and this guy is in the Z plane. So they're never going to intersect with each other. And remember, you have the nucleus in the center, so they're revolving around that nucleus in this shape, right? And then you have this guy, your 2s is going to be in the center of that. And so they're going to be revolving around that 2s structure, right?
Okay.
So you're just going to be literally laying layers on top of layers on top of layers. And so even though it kind of shows it as a ball with a very tight point, it's not that way. So because that tight point represents that energy level that will be below it. Does that make sense?
Yeah, it makes sense, but I still need like, probably I'll just go and watch an animation on YouTube.
So for instance, okay, you guys know the Russian dolls?
Russian dolls? What did you say?
Russian dolls.
Yes,
doll.
dolls. Yeah.
Where you
Okay, I
have
actually don't know.
you'll have a doll outside of a doll, outside of a doll, outside of a doll.
Mhm.
So that's essentially what you're doing here, right? It's a layer of dolls.
Oh, okay.
So that center is going to be the nucleus, and you put a doll around that nucleus, right? So you're hiding your really valuable thing in the middle.
Oh.
Just another
Oh,
doll.
okay.
Right?
Okay, that's better. Yes.
Yeah. Okay.
Yeah.
So, and that's what's happening. So, like I said, this is the p orbital, this is the d orbital, and the f is kind of like crazy. We typically don't go that far into it so much. Okay.
Right.
Yeah.
Nesting dolls. Thank you. Yeah, Russian nesting dolls.
Okay.
F would be on the outside if they're right.
So yeah, the f orbital is kind of crazy. So it's very, very complicated. So typically, and there's images of it, but it's just so complicated mathematically that most people are just, okay, there's the f orbital, right? So, but this is kind of an idea what they look like. Okay, so here, this would be the 1s. This guy would be the 2s. This guy would be the 3s. So you guys can see it gets bigger the further out you go, right? So that's also the size of the atom, right? So as we go down, the size gets bigger. Does that make sense?
Mm-hmm.
Yeah.
And I think we talked about that already, right? I can't remember.
How can it reach in all the way into the middle to get that electron that it needs?
That's the point. It doesn't reach in. Now think about it. So, and I used this as an analogy last time, right? So if you're going to be another atom or something like that, and you want to take an electron, right? So, and I always use the analogy of a pervert taking a kid, right?
Oh, yeah.
You're going to take the kid that's right next to the mother, or are you going to take the one that's, ran across town?
Yeah.
Oh, okay.
Okay. Well.
So the nucleus is kind of like the mom, right? So if the nucleus is kind of like the mom, the electrons that are closest to her are going to be really tight to her. So you're not going to want to take them. Those are going to be really hard to take. They take a lot of energy to take, because could you imagine trying to take a kid from its mother, right?
So, I mean, with that in mind, when you had the math up earlier, we -1 from the S and we put it into the N. So how come we didn't take one from like the closer one?
Okay, so you're still not looking at it, right? So why would you take it from the closer one?
No, I mean, S is closest to the nucleus, right?
Yeah, so, well, S technically, well, okay. Not necessarily. 4S,
Okay.
right?
I think that's where I'm getting
Right. So
lost then.
4S, the 4 represents the energy level, right? And then you have the 3D. Okay, so when we talked about the energy levels, we had the 4S and we have the 3D. Now, these guys kind of overlap each other. 3D is technically in that lower energy level, but it's a little more energy, just a little bit more, right? So it fills this guy up first, typically, and then it goes here and fills this guy up, right? But in terms of energy levels, there are little tricks that makes things a little bit lower. So if I have all these guys filled with 1 electrons, right? These guys, it'll be a lower energy level than having 1 here, 1 here, 1 here, and 1 here, and having 2 there, right? So this guy takes more energy to kind of keep it like this, because you have this one spray guy. So what it will do, it'll kick this guy up to here. So let me erase this. So rather than, these are 2 examples, right? In different. So okay, so the green is what we would expect, right? But the red is what actually happens. So in the case of, let's use, yeah,
Right. So the green is what happens.
yeah.
So,
No, the
but
green
the
is not what
green,
happens. No, the red is what happens.
I mean, the red is what happens and the green is where it was prior.
Yes.
But the green, isn't the nucleus on the left of that?
No, no, no. So the nucleus, so you got to remember, we're talking layers, right? The nucleus is not on the left of that. These guys are circling the nucleus. This is just drawing it. So the nucleus is in the center. These are just representing the electrons, right?
Right. But those electrons are, you know, orbiting around the nucleus.
Okay, so here's
And
the
since we took, so S, wouldn't S be closest? S group?
okay, so in theory, the 3s would be closer than it, right? So if we went down, these guys,
Underwater.
right? Can you guys see this? So here's the nucleus. This guy
Yeah.
represents the nucleus right here. So this would be the first energy level. So in that first energy level, we have just an S, right? So there's just the S. In the second energy level, right? We have,
You're muffled.
I said in the second energy level, we have one, we'll have the S, and we'll have a P. And the second one, right? So both of those are going to be in 2. Then we'll have 3. In the third energy levels, there's the S, there's a P, and there's a D, okay? So this will be your 3S, this will be your 3P, and this will be your 3D, okay? Okay, so now when I say closest to the nucleus, the 3S is closer than the 3P to the nucleus. And
Oh,
the 3S is closer than the 3D. Now, here with the 4S, so the 3D is kind of like this outer bounds. And so there are parts of it, I'm going to draw this in a different color. So when we get into that 4, there's parts of that 4S that will overlap with the 3D, right? So 3D really kind of overlaps the 4S in parts. Okay, they overlap a little bit, just that 3D does, but it only laps the 4S, right? So, but in terms of energy, it's more stable. This configuration, having it like this, where you have 2 in the 4S, and then you have 4 electrons here, rather than having your 5th electron occupy this one, having this empty spot messes up with stability. It doesn't give it balance, right? So since it doesn't give it balance, it prefers to sit there and do it like this, taking that 1 from that 4S and putting it up in the 3D. 3D is really in the third energy level, right? So part
Right,
of it
I see
is
it better this way.
lower, but part of it is bigger. Does that make sense?
Yeah, it's better laid out this way.
Yeah. Well, but you got to think of it both ways. Like this just kind of gives you where everything is supposed to be, right? It doesn't give you the
Right,
actual
yeah.
location, but really they're orbiting each other, right? This is a simple way of looking at the orbits and then not going through all of the different structures, you know? But you kind of need to think of it both ways, right? And so the idea is
Right.
that you want to try to find the lowest possible energy level, you know, at the end of the day. And they find that the electrons, they say, well, this is a lot lower in energy. It takes less energy to kind of keep this because it kind of keeps these guys all kind of even, you know, and not acting a little bit crazy. Having this empty spot causes it not to be even, you know? Okay, does that make sense?
Yeah.
So
What is this called again?
again, this guy is all called electron configuration. It's called electron configuration, but the
Okay.
process of this. Now, these are exceptions. So for instance, exceptions are going to be chromium, it's going to be copper, it's also going to be molybdenum and silver. So all of these guys are going to want to pop up, take an electron from that S subshell and bring it up to kind of level it off. Okay. So because it's more stable for it to have one electron in each orbital than just having that one empty. Okay. And again, those are exceptions, right? For the most part, they kind of follow the general rule that we say. So if you had given me this guy on an exam, I'd have been like, okay, cool. You know, I'd accept it because they're exceptions. Okay. Do you understand what I'm saying?
All right.
And so for the level
Yeah,
that you
with more
guys are at,
practice too.
yeah, and for the level that you guys are at, it's something that, you know, electron configuration is important to kind of understand why things are bonding and to kind of set up how things are going to behave and what valence electrons are. You guys are really looking at it in terms of valence electron, right? You guys are not looking at it in terms of, you know, well, we can kind of use this to do this, you know, in terms of making energy, or, you know, you're not looking in that regard yet. Okay. So
Okay.
it's just, we're trying to get you the basics first. Okay.
Okay.